Welcome to this video where we're going to have a look at Europa, which is one of Jupiter's moons, and it's thought to have these plumes coming out from its surface. And originally it was thought to come from a global, fairly deep ocean beneath the surface, but that might not be the case anymore, and it might be coming more locally from parts of the actual ice sheet itself, from the actual crust itself. So we're going to have a look at that and even compare it to Enceladus, which is a moon of Saturn and is fairly similar. It has similar sorts of plumes as well. So if we have a look at Europa, it's one of the Galilean moons. Its surface is frozen and it's not covered by craters, which means that there is some process there that's replenishing it, and it's likely active. So it's getting rid of any craters, any impacts that are occurring. So unlike other moons, like our moon, that's not active at the surface at all, it's got lots of craters. Here you've got this frozen moon which is replenishing its surface, so we don't see any real craters there, but we do see some of these structures. You can see like cracks and that, fissures, and this is due to tidal interaction with Jupiter, which is stretching and squeezing, which is cracking that surface. And when you have a look at Europa, you can also see some plumes. Now, this was taken with, I believe, the Hubble telescope and the Galileo spacecraft combined together to produce these images, along with the suspected plumes highlighted there. Now, they're not in very great detail because we haven't had a spacecraft orbiting it in much detail like we do with Cassini. So Cassini was orbiting Saturn for a long period of time, and it got very close to Enceladus, and we have much better images of the plumes and details about that, whereas Europa, we don't necessarily have huge detailed images of that. So here we have got evidence that plumes are occurring, that material is being thrown out from the surface. And Enceladus, again, we've got much better information here, but it's fairly comparable to Europa. It's a frozen moon, but it orbits Saturn instead of Jupiter this time round. It's got similar sorts of cracks on its surface due to being stretched and squeezed by Saturn. It also has fairly significant plumes. So Cassini's got quite close and has imaged these plumes in quite a bit of detail. So you can see they've got these plumes being thrown out into space, which again are also thought to come from a deep global ocean of the moon. Now, the location of those is from these cracks or fissures actually on the surface. So here you've got the tiger stripes of Enceladus, and if you were to kind of move around and look edge on, like you've got on the zoomed in bit there, you'd see those plumes originating from there. And these are weak parts in the crust where it's been cracked, and then material from lower down, or the liquid, as it made its way out, it's been thrown out in these plumes. And the same thing is thought to be occurring on Europa. Despite us not having as detailed images or information about the plumes, it has a similar sort of structure. It's got these cracks and fissures there, and again, these plumes are thought to originate in those sorts of locations as well. Now, how do we know there's a global ocean there? So we can see those plumes. We can make some assumption that there's water underneath that is then making its way up through these cracks and being thrown out into space in these plumes. But there are other ways which we can confirm that there's a global ocean there. Now, one of those is oscillation in the rotation of the moon. That can normally hint to an internal ocean. So what do we mean by an oscillation in its rotation? Well, as these moons go around their planets, so I'll give the example of Enceladus here going around Saturn, they rotate, but they also go around the planet as well. Now, because the orbits are not perfectly circular, they are elliptical, it means the rotation of the moon speeds up and slows down ever so slightly. So it's not a constant rotation due to its slightly elliptical orbit. Now, if you've got liquid internals, like a global liquid ocean, then the solid surface takes some time to catch back up with the core. So if it speeds up, slows down, there's kind of a lag there, and it causes a wobble in its rotation. Now, if it was purely solid, that wobble would be less significant. So the fact that it's wobbling quite a lot more than if it was expected to be solid, gives us indication that actually it's got a fairly large liquid ocean for these moons. This is one of the ways we can determine there is an ocean below the surface without actually seeing it. Another way is if you've got spacecraft moving nearby, so if they're orbiting it or they pass by, if you've got a perfect orbit, it will take a normal orbit shape. But if you've got a uneven distribution of material underneath the surface, so different densities, different masses there. As it passes nearby, it receives a slightly different gravitational force and it perturbs that orbit slightly. So this is very exaggerated, but if you had a spacecraft moving by and the different internal structure would slightly alter its orbit, so you can see that it's not quite perfect, and those sorts of gravity measurements from spacecraft can help us look at the internal structure of a moon or planet, and that's how we've got a pretty good idea what the internal structures are of a lot of the planets, because we put spacecraft in orbits and their orbits, they deviate ever so slightly, which allows us to work out what's inside. So that's another way. I mean, an example is if you've got a very large mountain and the spacecraft passes over just ahead of that, there's going to be more material there, so the gravitational force is slightly more than on like a flat part where there's less material there. So actually the orbit would be pulled ever so slightly because of that. So little things like that can help us determine the distribution of mass internally and on the surface, things like that. Now, it was originally thought that these plumes are originating from deep ocean. So this is an illustration of Europa. You've got that thick icy crust there, and they come from the ocean in these cracks, and then you get these plumes coming out. But that might not be the case, at least for some of them anyway, and that you could have some melt material in the sheet itself, which is then coming out as a plume. So it actually originates in the sheet as opposed to the ocean, which is further down. Now, why might that be occurring? Well, the example with Europa is if you had an impact. So this is a minor object, like an asteroid or something, that has then hit the surface. It's melted the surface, and as it starts to freeze, you then end up with pockets of melt material below the surface. And what happens there is, it's kind of like a brine. It's not fresh water. The actual surface or ice shelf is quite salty, and you get these pockets of brine that migrate in the sheet that were originally melted. They then refreeze and they become pressurized as a result, and then they actually rupture, and then you get the plume, and it's a more localized plume than coming from deep down underneath. This could be one of the methods that's causing the plumes on Europa. It doesn't necessarily mean that it's the only mechanism that's doing this, but it has been identified as one of the sources of some of these plumes, which has significance really, because if they're coming from the ice sheet, it has implications for life. If we test what's coming out of here, it doesn't necessarily represent what might be deeper down in the ocean. And it could also work with other moons as well. So Enceladus, maybe some of the plumes there originate from similar things as well. Although we do know with Enceladus that there are quite deep cracks there, like the tiger stripes, where these plumes are originating from. But maybe some do originate with this particular method as well. Thank you for watching, and if you enjoy, then you can check out some of the other videos.